Hey everybody, maybe I'll pause that. This is a video for my Intro to Calc class. This is our introduction to chain rule, and I thought what better way to get us into chain rule than to play a song that has the word chain predominantly in the title. So that was of course Chain of Fools by the late great Aretha Franklin. If we had regular classes going on right now, I'd for sure do this lesson and then give you a work period the next day to work on the homework, and for sure I'd have had a whole playlist for you of songs that have chain in the title just to make your lives more interesting. Now, the other thing we'd be doing if we had regular classes is warm-ups. Remember how you'd come in the morning and I'd have a warm-up on the board? Well, here's today's warm-ups. Why don't you take a sec, pause the video, and give those a try. And we'll join you again in a second. Did you get them? All right, let's do A together real quick. So for A, let me just move some things around here. I guess I should have said maybe coming in that the reason I put the differentiation rules here is that I want you to only use these ones. If you already know how to do this with the chain rule, by all means, try to resist and use just the regular rules here. Now, if I'm going to use the regular rules on this, there's actually two ways I can do it. I can expand this thing. And if I expand this one, I get, let's see, square the first, times the two together, and double it, and then square the last. So now I'm basically using my sum rule here, and basically each one of these is its own function. And f prime of x is 16x cubed plus 24x. Now, that's of course in its simplest form. I'm actually going to go backwards on this and put it into its factored form, just because I want to show you something about that. I want to show you that in its factored form, this thing looks like this. I can take 8x out of both those things, leaving me 2x squared plus 3. And I'm even going to break this 8x up. I know that's the simplified factored form, if there is such a thing as simplified factored form. And I just want to show you that this thing can look a little different. It can look like this. And what I wanted to show you about that is there's something kind of interesting about this form. This too corresponds to that exponent. This 4x corresponds to the derivative of what's inside the brackets. And of course, this here corresponds to the bracket to one less power than the power we started with. Isn't that interesting? Okay, let's try B now. See how we did with B. Again, I'll keep those kind of handy in case I need them. Well, let's see, for B, again now it's f of x equals 2x cubed plus 3, all cubed this time. All right, well, if I'm going to expand that, that means I got to cube this thing, which means I got to take that thing there and then times it by another 2x squared plus 3. Oh, this is a squared, not a cubed. Oops, mistake. And then times it by another 2x squared plus 3. Or if I've met people who can just look at these and they know binomial expansion so well that they just rattle them off. I'm not that good at it, so I actually did work it out ahead of time. So it is 8x to the 6 plus 36x to the 4 plus 54x squared plus 27. All right, and if you're wondering how on earth would anybody do that that quickly, if they really could do it that quickly, and again, I'm not one of them, it's because they know something, they've memorized a pattern to binomial expansion that you'll learn more about in grade 12. But the more steps there are, the higher this power is, the more of a drag this is. Once I've done this, once I've gotten that out of the way, well, the next step's pretty easy. 6/8 is 48, and then x to the 5. 4/36 is 144, 2/54 is 108, and as always, the derivative of a constant is nothing. So looking at that, can I make this somehow look again like some version of that, the way that I did for the first one? And the answer is yeah, I can. Once again, take out the greatest common factor here, factor it out, which would be 12x. And then you'd be left behind with a 4x to the 4 and a 12x squared and a 9. And if you look at that closely, that's actually just this squared. I mean, remember, that's what we had at the beginning of A. So again, I can change this to 2x squared plus 3 all squared. And even the 12x I can kind of break down. I can break it down into 3 and 4x. And once again, this exponent corresponds to that coefficient. This term here, or this factor here, sorry, not term, factor, this factor here corresponds to the derivative of what's inside the bracket. And then this factor here is really just this entire thing, but I've taken the exponent and subtracted 1. And now we're going to show that with the chain rule, which is what we're learning next, that actually is the way that you can do anything along these lines. This is actually something that we can generalize as a rule. And if we generalize it as a rule, hang on, I got so many cords in my way here. Cords, calculators, you name it, it's in my way. Alright, there we go. Okay, so before maybe we leave these warm-ups, did anybody here do them a different way than me? Because I did say you could use anything on here. And you know what else is on here, of course, is the product rule. Let me just do, so warm up 2.0 here. If again f of x is 2x plus 3, or sorry, 2x squared plus 3, and I have that all squared, I can rewrite that as 2x squared plus 3 and 2x squared plus 3. And then for my f primed of x, I can use my product rule, where I would say that it's the derivative of the first thing times the second plus the derivative of the second thing times the first. And if you have the same thing twice, you could just say that you have two of them when you're adding something to itself. And again, that gets us back to the original exponent, the derivative of the inside of the bracket, and the original function with one less exponent on it. And I could do the exact same thing with the example where we had the power of 3, but I think now let's move on to what the actual quotient, or what the actual chain rule tells us. And the chain rule, so maybe start a nice fresh new page of notes here. The chain rule is something that you actually have seen a couple times already. If you've looked at this little handout that we gave you, it's been in 2 different booklets now. And let's expose the chain rule here. There's the chain rule right there. Oop, I didn't fold that very good. I just failed at origami. There we go. I don't want you to look ahead yet. So there we go. There's the chain rule, which basically says that the derivative with respect to x of a compound or composite function, I should say composite, not compound, of a composite function is the derivative of the first function with its variable replaced by the inside function times the derivative of the inside function. In Leibniz notation, which granted we don't use that much so far, but we'll start using it more as we get into more complicated things. In Leibniz notation, you can say if y is equal to some function with, we'll say, the function of u, and that u is equal to g of x, then the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. And let's just remember when we look at it this way, this is the way I tend to think about it more than more often than not, but Leibniz notation is the same rule, same basic idea. Remember when you're looking at it though, that this isn't a divide. Every time I show somebody this, they go, well, why don't you just cancel the du's? Well, that's because this is not a divide, just like this isn't a multiply, right? This is not something f times u. This is the function of u. This is a slope of a curve, right? So these are not really divides, right? That says the derivative of y with respect to u, the derivative of u with respect to x. This line doesn't mean divided by right now. It means with respect to. Same way that this bracket means of the variable, or the function with the function of variable u. Okay, so the chain rule, as a rule, looks like that. Let's do a couple of examples that hopefully kind of illustrate what it is that it looks like. For example 1, we'll use something even simpler than the warm-up. It'll be similar to it, but let's knock it down to being linear. And then let's have another function that is, maybe this one will be a quadratic. There we go. So I have two functions, f of x, g of x. Notice those two functions are definitely differentiable anywhere. And what I want you to do is I want you to find, remember this notation from the last lesson? F of g primed of x. In other words, I want you to find f of g of x and then find the derivative of it. In Leibniz notation, I'm asking you for the derivative with respect to x of f of g of x. So let's see what we can do with that. How about for starters, why don't we actually start by finding out what f of g of x is? So f of g of x is replace the x in the 2x with the other function, x squared minus 1. And we can work that out. That's 2x squared minus 2 plus 3, which is 2x squared plus 1. That wasn't very hard. And then I would like the derivative of that. So f of g primed of x is, well, the derivative of 2x squared is 4x, and the derivative of 1 is nothing. So that's the final answer. But we now have a shortcut. We can now use this formula that tells us that I can say that the derivative of this thing is, I'll just write the formula again since it's way up at the top. The derivative with respect to x of f of g of x is the derivative of basically the outside function with the inside function tucked into it times the derivative of the inside function. Okay, so let's see what we can do with that. We can say, all right, well, going back to the original function here, f primed of x would be just 2. And it's okay. If I want to plug g of x into the variable when all that I have left is 2, well, then I'm just going to have 2. So this thing here is just 2. And then g primed of x would be 2x. And 2 times 2x is 4x. And you might be looking at that going, well, big deal. This wasn't a whole lot less work than this was. But think about how complicated a composite function could get, where you could be putting something like this into something that had an x to the power of 4 and an x to the power of 3 and an x to the power of 2. And by the time you've replaced all those variables with this, you're going to be very lucky if you didn't make any sort of mistake. So doing it this way is probably an advantage. Even if we did this backwards, using the same two functions, what if instead of f of g of x, I asked you to find g of f of x primed? In other words, the derivative of the composite function, but I go the other way. And I'll do it both ways here. I'll go g of f of x and actually figure out what it is. So that would be, again, let's take a look at the two functions, make sure we remember them. That means that I'm going to take g of x here and plug in this function to the variable x. Okay, so let's do that. Bring back my rules here. Don't want to be too far away from my rules. So let's see, what am I doing again? Oh yeah, I'm plugging in f of x into g of x, which means that I take 2x plus 3 and square it and minus 1. Okay, that's not too hard. That's going to be, expand that, square the first, times the 2, double it, and then square the last, and then minus 1. And I get 4x squared plus 12x plus 8. So the derivative of that, the derivative of, with respect to x, of g of f of x is, well, again, I can just use the sum rule here. So that's going to be 8x plus 12. And derivative of 8 is nothing. So that's my answer. Okay, now let's use the chain rule. And try the question again. So with the chain rule, I am going to say that, of course, that I want the derivative with respect to x of g of f of x, which would be g primed of f of x times f primed of x. So let's see what that would look like. So g primed, so let me just write down what my functions were in the first place again. They were that f of x is 2x plus 3, and g of x was x squared minus 1. So g primed of x is just 2x, but I'm plugging into the 2x what f of x is. So that's going to be 2, and instead of x, 2x plus 3, times f primed of x, which is 2, and notice that's going to be 2 times 2 times 2x, and 2 times 2 times 3. And I don't know about you, but that one felt like less work than the other way. So that's the basics of chain rule. And I'll just get into kind of one more kind of application, if you like, or one more kind of complication to this. We're going to add the chain rule to, actually I'll just start on a new page. We're going to add the chain rule to the power rule. And does everybody remember the power rule? So we'll say recall the power rule. And of course the power rule says that if I have some function f of x where it's just some monomial of x, I can say that that f primed of x is, take this exponent, make it the coefficient, and then subtract 1 from the power. Putting into more Leibniz notation, if u is equal to some function g of x, then d by dx of that u to the power of n is n times the function u to the power of n minus 1, all times by dy dx. So that's the power rule. And to put it in with the chain rule now, I'm going to say that it's going to be the derivative with respect to x of, I'll say again g of x, because g of x could be substituted for u, to some power of n is equal to n times g of x to 1 less than the power times the derivative. And if you were paying close attention to the second way that I did the warm-ups, this is exactly what we got when we changed them to factored form. Let's go back to them. For example 2 here, for our chain rule. Oh, and I guess I can now reveal the rest of the chain rule, because that's what it says on your chain rule or your list of rules. It has power rule, then power rule plus chain rule. So I folded that better than I thought. There we go. Ta-da. So let's go back and do this as example 2, and we'll go back to f of x is 2x squared plus 3 all squared, and I would like to find f primed of x. Okay, well, the first thing I can do is I can call the thing inside here g of x. And so the derivative of function f with respect to x, or f primed of x if you like, is going to be the exponent. Just again, I'm just using this formula. So it's the exponent n times the inside, or the original function with one smaller exponent, so minus 1 from that exponent, so that's 2x plus 3, and then minus 1 from the exponent, so that's now a 1, times the derivative of the function that's actually the inside of that bracket, so that would be times 4x. And I can simplify that a bit. 2x times 4x is 8x, and 2x squared plus 3, and I'm sure you'll agree that that's less work than it took to multiply that out. And if I call this A, of course example 2b would be where this was a higher power. 2x squared plus 3 to the 3, find f primed of x. And notice it doesn't really matter to me how big that power is, because I don't have to expand it out anymore. It's just a very simple application of this cute little rule. The 3 becomes a coefficient there. Then I take the derivative, I take the inside bracket and just take it to one less power than it had before. Then I times by the derivative of what's in the bracket. And you'll notice that's what we got when we did this example the first time. So I'll just put the two coefficients together here. All right, so there's the question that we started with. And just to kind of show you where you can go with this, just to kind of prove what I said a minute ago, what if for the same original function, I just took it to an even higher power, and suppose it was 2x squared plus 3 to the power of 8, and I'd like to know what f primed of x is. Well, again, it shouldn't scare me that that's such a big power, because I don't really care. The chain rule works just as well. No matter how big this power is, the 8 becomes the coefficient, and then that's now a 7, and I times by the derivative of the inside of the bracket, which is 4x. Okay, and then that's going to give me f primed of x is, and I'll just make that 32x times 2x squared plus 3 to the 7. Think about how long it would have taken to expand this to a power of 8, and then have gotten a great big long answer, and then to try to factor it back to this if I wanted a factored form. Okay, so last part of this example, here's one. I mean, you might be saying, well, I still could have spent 20 minutes of my life and actually figured out what this is to the power of 8, but what if f of x had been a radical? And these were the questions that in the earlier assignments I had you guys kind of skip because we hadn't shown you how to use the chain rule yet. You kind of need the chain rule for this, because most of you have no problem saying that, yeah, I can change that to an exponent instead of a radical. But unlike all the previous examples, even this ugly one here, if I had enough time and scrap paper, I could come up with what this is expanded to the power of 8. But how do you expand a fractional power? How do you times this thing by itself a half a time? Well, the answer is you don't. You use the chain rule. So the chain rule says this becomes the coefficient, then this, remember that this is now 1/2 minus 1, I'll do that in 2 steps, and times 4x again. All right, now the next kind of trick to this is simplifying it properly. I'll take a second and do that subtraction. So that's now 2x squared plus 3 to the power of negative a half times 4x. And all right, let's see, what can we do with that? Well, I think what I will do with that is I will take the 4x and times it by half. Remember, if you're timesing three things, it doesn't matter what order you do it. So a half of 4x is just 2x. And remember that a negative exponent makes it a reciprocal, and then I'll change it back to a radical. Now, why am I changing it back to a radical? Because the question started with a radical. So generally speaking, if it started with a radical, it's going to want an answer as a radical. Some textbooks will usually use a rule that if it's anything more complicated than a third or a fourth root, they'll just leave it as a fractional exponent. But either way, they'll usually won't leave it as a negative fractional exponent. So you'll still have to do that reciprocal step. One tool that I've shown you before, that if you're doing your homework and you get an answer and then you look in the back and go, oh, that's not the way that the answer in the back looks, before you even start to play with your answer and see if maybe all you need to do is simplify it a bit to get their answer, you can see if you did it right by going to Desmos, graph the original, right? Call it f of x, and you'll notice that, okay, so it's this curve, and it's always nice to kind of refresh your chapter 1 skills. It's like, okay, what will this thing look like when I want the slope of its equation? Well, let's see. Everything here has a negative slope, and gee, it's almost linear, so it's going to be almost a horizontal line, and then it'll kind of swoop up and hit 0. So I'm thinking it's going to be almost a horizontal line. It swoops up, it hits 0, and then it becomes a positive almost horizontal line. So that's what I'm expecting, and that's what I get. Now, is this, the thing that I got, the same as that? If it isn't, I didn't do my derivative right. But as you can see, yep, we did it right. And feel free to do that on any of your homework answers. That'll kind of save you on coming to me with the question that, hey, I got this answer and it's not the same as the back. It's possible that maybe you're just not seeing the way to simplify it. But you might actually have the right answer. If your graph was different, then you don't have the right answer. Okay, let's do one more example and then we'll turn you loose for the day. We'll call this, I've kind of forgotten what my numbering is. I think I'm on example 3, but I don't remember. If I'm not, you can fix that yourself. Example 3. Let's use more Leibniz-y notation this time. If y equals x squared minus x plus 2, we'll also do a trinomial instead of a binomial, and we'll use the power of 8 again. I don't know why, but I like the number 8. This time I will say find dy by dx, just to throw in some Leibniz notation. Okay, so once again I can say, all right, I'm going to let this inside bracket be a different function called u, and u is of course going to be a function. I'll give it a different lettering. I'll call it g of x. Of course n here is equal to 8, and I have of course the formula that dy by dx should equal, in Leibniz notation, it should be the n times u to the n minus 1 times du dx. So there's the Leibniz notation. So okay, let's follow it. So n is 8, right? That's the exponent. U is of course this thing to the power of now 7, and du dx, which means the derivative of g of x, is 2x minus 1. And you could, if you wanted to, times 8 by 2x minus 1 and then just leave that as the power of 7. Or I'm actually pretty happy on a question like that if you just leave it the way it is. Okay. Sometimes it's easier to mark them if people don't simplify them. Okay, so that is basically the chain rule. Check the blog for the assignment. We won't hit you with a ton of questions for the first lesson here. Mr. Lacko will do the next lesson with you where we'll start using the chain rule on some more complicated applications, like combining it with the quotient rule, for example. Okay, thanks for watching, everybody.